So welcome back for the third lecture of this week. In the last lecture we had discussed top-down and bottom-up parsing approach, and then finally we came up with a dynamic programming approach of using CKY algorithm, and we converted a grammar to Chomsky normal form. So now once my grammar is converted to Chomsky normal form, how does CKY algorithm work? So this is the idea. So I will take a sentence. I have n words in my sentence. So you will think about n plus 1 lines that are separating them, starting from 0 to n. Okay, and so once you have done that, any xij will denote words between line I and j, and so you will build up a table such that any xij will contain all the possible non-terminals that can derive words between the lines I and j. Okay, and you do that bottom up. So what I am saying, you have word 1, word 2 up to word n in your input string. So we'll assume some lines like 0, 1, 2, n minus 1, n. Okay, so for example x02 is words w1, w2, and so on. So now what you will do, you will build up a table. Okay, and table will be some sort of triangular table. So this can be 0, 1, 2. So this element will denote x01. What are all the non-terminals that derive this word between 0 and 1? Similarly here you will write x12 and so on. Suppose there are only 3 words, so this is x23. Okay, so we will write down all the non-terminals that derive this. You will first fill this, then you will go next step x02, x13. Okay, and once you fill this, you will use x03, the final one. Okay, now what is where are we using the fact that this grammar is in CNF, Chomsky normal form? I'll make use of the fact that at any point this can come from only 2 non-terminals or a single terminal. So at this point, when I am seeing at an individual word, so 01 will always be an individual word. Similarly for 12. So this will come by a rule, capital A goes to small a rule of this kind. Okay, so I'll find out all the non-terminals that derive this terminal. That's how I will fill the diagonal elements, the first diagonal elements. Next time, this cannot come from a single terminal because there are 2 words. Okay, so this has to come from 2 non-terminals. So I'll find out if there is a rule that gives me these 2 non-terminals, and that's where I'm using Chomsky normal form. Okay, so finally when I'm here, I'll see if the sentence S generates the whole sentence. So I'm caching all the possible intermediary steps here, so that I do not have to do certain again and again and again. Okay, so this is a simple homework exercise. So in the last lecture we had given you a grammar in Chomsky normal form. Now take the sentence, book the flight through Houston, and use the CKY algorithm to find a parse tree for that. Okay, but what I will do an example in today's class also, so that you become much more comfortable with using CKY algorithm. So let's take this example. A pilot likes flying planes, and the grammar is given to you. Okay, so let's do that in the way I had explained. So 0, 1, 2, 3, 4, 5. There are 5 words. Okay, and this is the line. And now you should understand how do we denote these elements. So this is x01. This will denote only the first word. This is x12, x23, x34, x45. This will be x02, words between 0 to 2, x03, x04, x05, x13, x14, x15, x24, x25 and x35. Now I have to fill here what are different non-terminals that fill each of the individual elements. x01. What is x01? My word is A. So a pilot likes flying planes. So is there a non-terminal that derives the word A? And if you see the grammar, dt derives A. Okay, so you can fill in dt here. Dt derives A. Pilot, NN derives pilot. Likes, VBZ derives likes. Flying, so you see there are two non-terminals, VBG and JJ, they derive this. And planes, NNS. Okay, so filling the diagonal element is very easy, the first diagonal element. Then you go to the next step, x02. Now x02 can come from x01 and x12 as a breakup of these 2 points. So is there a non-terminal where, or is there a rule in my grammar when the right hand side I have dt followed by nn? And if you see your grammar, yes, np gives me dt followed by nn. So I can fill in np here. x13 comes from x12 and x23. Yes, x13 is pilot likes, so it comes from pilot and likes. So any non-terminal that gives me nn followed by vbz. And if you see, there is no non-terminal, so I will fill in empty here. Similarly, anything for vbz followed by vbg? No. Anything from vbz followed by jj? x35. vbg followed by nns? Yes, vp. And jj followed by nns? np. Okay, so there are 2 possibilities here. So fine, this row is done, this diagonal is done. Now we go to the next step. Now how do I derive x03? A pilot likes. Now that's why I am using the Chomsky normal form. I cannot derive it as a sequence of 3 non-terminals because each individual non-terminal can give me at most, not at most, exactly 2 non-terminals. Okay, so what are the 2 places from which it can come? So one possibility is I can break x03 as x01 and x13, 1 word and 2 words, or x02, x23. There are 2 possibilities. Okay, so I have to check each of these possibilities. x01, x13. So x01 is dt followed by null. So this is already gone. Okay, this is no non-terminal. x02 is np followed by x23 is vbz. So np followed by vbz. Is there a non-terminal when the right hand side I have np followed by vbz? Okay, and if you see your grammar, there is nothing. So this is also null. So here it is null. There is no non-terminal that can derive a pilot likes. Okay, now pilot likes flying, 1 to 4. So again 1 to 4 will be 1 2 2 4 or 1 3 3 4. So 1 2 2 4, 1 2 is nn, 2 4 is null. So this part is null. 1 3 3 4, 1 3 is null. So this becomes null also. 2 5 will be 2 3 3 5 and 2 4 4 5. So 2 3 here is vbz and 3 5 is vp. Is there something with vbz and vp? Yes, vp. Gives me vbz and vp. 2 4 4 5. 2 4 is null. Okay, so this is my VP. Similarly, now you will go to X04. Now, what are different ways in which you can break X04? Now, 04, again you have to break it in a sequence of two non-terminals. So, it can be 01 followed by 14 or 02 followed by 24 or 03 followed by 34. The three ways. So, let us see one by one. 01 is DT, 14 is null. So, this part is gone. 02 is NP and 24 is null. This part is also gone. 03 is null already. So, this is null. Okay. 15. 15 can be 1225, 1335, 1445, 12 and 25. Yes, NN followed by a VP. So, is there something in my grammar NN followed by VP? No. So, this is gone. Similarly, 13 followed by 35. 13 is null. Okay, and 13 is null, so this is gone. 14 followed by 45. 14 is null, so this is also gone. So this is also null. Now the only thing remaining is X05. Now how can I fill X05? What are different ways? So let me write down here. 05 can be 01 followed by 15, 02 followed by 25, 03 followed by 35, 04 followed by 45. Okay. 01 followed by 15. 01 is there, 15 is null, this is gone. 02 followed by 25, 02 is there and 25 is also there. This is NP followed by VP, and this is a sentence in my grammar. So S gives me NP-VP. So this is one possibility already. So that means this sentence is grammatical at least. There is one S that derives this. But are there any further S? So for that we have to look at the other possibilities. 0335. Okay, this is null, and 0445 is null. Okay. So fine. So we see there, I think we made one mistake here. There should have been another VP in this case. Okay, so there is VP1, VP2, and then there will be S NP VP1 and NP VP2. So yeah, I will suggest that you look back in this calculation we did and see where we made a mistake. Okay, but everything else is the same that we did here. So there are two different S in which this sentence can be passed, two different ways. So now, once you know this, I'll say that use the previous example. So that is, book the flight through Houston from the other grammar and try to get its pass tree. So now, in this example, what we saw, there are two possibilities. So, can you think of the possibility, why there are two possibilities in this case? A pilot likes flying planes. Okay. So, whether he likes to fly the plane or whether he likes to see flying planes, something like that. So, there are two different interpretations. That's why there are two different passage of this sentence. So, each individual pass will denote one particular interpretation. Now, by using this context, by this CKY algorithm, find out all the possible pass trees using my grammar. But I have no way of saying which pass is more probable than the other pass. I cannot assign some probabilities to them. Okay. So, something, if I have, so this sentence, the man saw the dog with the telescope, it has two different interpretations in terms of two different passages. Whatever I have covered till now, it cannot tell me which pass is more probable than other. So now, we would like to have a way in which we can assign them the probabilities, that this pass is more probable than other. And for that, what we use is called probabilistic context-free grammar. So this is a simple extension of context-free grammar, where in addition to whatever we have seen in context-free grammar, each rule is also assigned some probability. Okay, so as you see in the formalism, it is T, N, S and R. They are exactly same as what we had seen in the context-free grammar, plus there is something called P. So I am assigning a probability distribution over the rows, and the only constraint here is that from a given non-terminal on the left hand side, the probability of generating anything should add up to 1. So if there are 5 possibilities, if I add all the 5 possibilities, the probability for all the 5 possibilities, they should add up to 1. Okay, so this is the constraint. So probability in the rule gives the probability of each rule PR. So the constraint is for all x in non-terminals, probability of x to gamma for all the possible gammas should add up to 1. Okay. So let me give you an example. So this is one simple simple PCFG in Chomsky normal form. So what do you see here? From S, there is only one rule. S goes to NPVP. Okay, so because there is only one rule, it has to have a probability of 1. From VP, there are 2 rules. VP can give me V followed by NP or VP followed by PP. So the constraint is that for the probabilities of these 2 rules should add up to 1. So that's what is happening here. The first rule has a probability of 0.7, second rule has a probability of 0.3. So these 2 add up to 1. Now PP gives me P and P, only one rule with PP on the left hand side. So this has a probability of 1. P gives me only with, again probability 1. V gives me SAW. This is a probability 1. Now all the rules on the right hand side are starting with NP. NP can give me NPVP or the words in lexicon like astronomers, years and so on. So all these should add up to 1, and you can see that this actually happens. 0.4 plus 0.1, 0.5, 0.68, 0.72, 0.9 and 1. So all these probabilities are adding up to 1. So this is the constraint that is being followed. The rules have the same form as in context-free grammar, but each rule has a probability. Now how does it help? It helps in that I can now assign probabilities to each individual parse tree. So suppose this is one parse tree. Astronomers, for the sentence astronomers saw stars with years. How do I find the probability of this parse tree? This is the parse. So I know S gives me NP and VP. Yes, this is the first rule that I am applying. Now as for my PCFG, the probability of this rule is 1. S giving NP VP is 1. So I have this 1 here. NP giving astronomers, deriving astronomers is probability 0.1. VP deriving V, NP is probability 0.7. V giving SAW is 1. NP giving NP VP is 0.4. NP giving stars is 0.18 and so on. These are the rule probability as per my grammar, as per my PCFG. So what I will do, I will just multiply all these probabilities. 1 times 0.1 times 0.7 times 0.1 times 0.4 times 0.18 times 0.18. This is my probability of this parse tree. And if I get a second parse tree, where instead of VP giving me V and P, VP is giving me VP followed by PP, I can again compute its probability by multiplying its corresponding rule probabilities, and I can find the probabilities of both the parse trees individually. Okay. So now, how do I use that to compute the probability of the tree? That is simply the product of the probabilities of all the rules that I use to generate this, and probability of a sentence. And the probability of sentence is nothing but find out all the parse trees and the probabilities of the individual parse trees and just sum them up. Okay. So probability of a sentence is the sum of the probabilities of the trees that have this as the yield. That is another way of saying that those parse trees are used to generate this particular string. So in the first case, I had the sentence and there were 2 parse trees. I can compute the probabilities of individual one. So PT1 and PT2 I can find out. And then to find the probability of the whole sentence, I just add up these two probabilities, pt1 plus pt2, and that gives me the probability of this whole sequence. Similarly, if I have another sentence like book the dinner flight, and as per a different grammar, I can compute the parse trees, the two parse trees, compute the probability for the individual one. Okay, so parse tree 1 here, book the dinner flight is 1.62 into 10 to the power minus 6, and book the dinner flight will have a probability of 2.28 into 10 to the power minus 7. So one thing I can immediately see is that the first one, parse, is a more likely interpretation than the second one. Let's look at some of the features of probabilistic context-free grammars. So why we started with this formalism? So we said that using the context-free grammar, given a sentence, we can find out all the possible parse trees, but we are not able to assign any probabilities to that. So by using PCFG, if for a given string the number of parse trees are increasing, I can also assign the probabilities for each individual parse tree. So that gives me some plausibility, which parse tree is more probable than the other one for the given string. So this is important, but at the same time, we should understand that although by using PCFG I can compute what is the probability of the sentence by taking all the parse trees, taking the individual probabilities and adding them up, this does not give me a very good plausibility of the sentence. Okay, this is only looking at the structural factors, not some lexical co-occurrence. So in general, to find the probability of the sentence, you would prefer to use language model than a PCFG. PCFG is good only for finding the probability of a parse tree, which parse tree is more probable than another one. Yes, if it helps in some cases, like in real text you might find some grammatical mistakes. So PCFG will allow that, but will give you a very, very low probability. So in one case you can also probably find out which sentence has some grammatical mistake if the PCFG is giving it low probability. And yeah, this is something that I said earlier. So in practice, this is not good for modeling the probability of the sentence. Okay, language model is much better than PCFG. So why is that the case? So a simple example is, if we have the same sentence, I have two different trees, one is smaller than the other, the smaller tree will always have a higher probability than the larger one, because all the probabilities are less than 1, and for a larger tree you are multiplying the probabilities. Okay. So yeah, the takeaway here is that, so you use PCFG to find out what are all the probabilities for different parse trees for a sentence, okay, and try to choose the best one. So now, once we have this formalism of PCFG, there are some interesting questions that we would like to explore using that. So suppose I am given a sentence W1M, okay, I am given a grammar G, and there are various parse trees, T is one of those. So what is the most likely parse for this sentence given the grammar? So which parse tree T gives me this maximum probability, argmax of probability given this sentence and the grammar. Okay. Then what is the probability of the sentence? Probability of the sentence given my grammar. And then finally, how do we learn the rule probabilities of my grammar G? These are the three interesting questions that we would like to answer in the next lectures. So for example, how do I find the most likely parse of a sentence? So one simple solution is find out all the possible trees and take the one with the highest probability. But is there any efficient method for doing that? What is the probability of a sentence? Again, I can find out probabilities of the individual parse trees, add them up. This gives me the probability of the sentence. But can I do it by exhaustively enumerating all that and adding it, or is there some other method? And finally, there is some interesting question that how do I learn the rule probabilities in the grammar G? And the answer to this will be similar to what we saw in the case of hidden Markov models. So there will be again two ways of learning the parameters. One will be when I am given the corpus and some labeled parse trees. I can use them to find the probabilities. Another scenario where I am given the corpus but not the parse tree. I am only given the grammar. Grammar in the sense CFG, not the rule probabilities. Then how do I learn the parameters? So this will be again very interesting topic. And there you can use some ideas that I had shown earlier for the Baum-Welch algorithm. So in the next lecture, we will start trying to answer some of these questions. Thank you.